All right, gang, Math 6620. The previous video, we left off talking, let's see, what did we leave off doing? It's been about an hour since I posted that. I got sidetracked, which happens. I think in the previous video, we got to the point where I show or demonstrated how to get the degrees of freedom. It's just in our case, it's 15, which is number of parameters that we estimate, well, number of variables times the number of variables plus 1 divided by 2. So we have 15 minus the number of specified model parameters, which again is each of the variance components. So there's 3 covariances, there's 6, we have 4 paths, there's 10, and we have 2 disturbance terms, which is 12. So 15 minus 12 gives us 3 degrees of freedom. Now, the 3 degrees of freedom being greater than 0 says that we can now take a look at these model diagnostics and determine if our model fits the data. So there are going to be 5 of them. The very first one that we look at, or that I want you to look at, is the chi-square. So this part right here. This is a standard test of hypothesis, where the null hypothesis is that the model fits the data perfectly. You can see in our situation where we have this chi-square test statistical and 3 degrees of freedom. We have statistical significance at the 0.001, well, 0.01 level. So we violate or we get statistical significance, and we reject the null, which tells us our model does not fit our data well. Now, these are things I should actually write this out, and that's why I'm kind of hesitating and stuttering and being all silly. I'm starting to second guess the way that I'm presenting this, but I'm going to stick with the plan. So what should you know about the first? There's going to be 5 of them. What should you know about the first model diagnostic? If the p-value is less than 0.05, our model, our sample data does not, or I should say our model, does not fit our data. So we have strike 1 against concluding that our model is well fit. The next thing we look at is the Comparative Fit Index, and where is it? Okay, so the Comparative Fit Index, the conventional threshold on it is if the CFI is greater than or equal to 0.90, then our model fits our data. We squeeze right in at 0.91, if you will, rounding to the hundredths. So this diagnostic tells us that we have a model that fits our data well. The next thing we would look at is the Tucker-Lewis index. The conventional cutoff on that is usually 0.95 or 0.90. I usually go with a little bit more conservative at 0.95. Either way, we are not above 0.95. So if the Tucker-Lewis index is above 0.95, then our model fits our data. Ours is 0.692, so our model does not fit our data. So strike 1 and strike 2. So we're 1 for 3 in terms. No, wait a minute. We had strike 1. We hit the mark there. Strike 2. So we're 2 out of 3, telling us our data does not fit the data well. I'm sorry, our model does not fit the data well. The fourth one is the root mean square error approximation. It's RMSEA. The conventional threshold there is, this is actually a model of bad fit, so we want a lower estimate here. I think the RMSEA needs to be less than 0.10, indicating a good fit. We are not below 0.10. Again, 0.10 is kind of the conventional cutoff. So again, we have a strike against believing that our model fits our data well. The final one is the standardized root mean square residual, and the SRMR, typically anything below 0.08 indicates good model fit to our data. So we squeeze in just below 0.08. So from this model diagnostic, we can determine that our data, our model does fit our data well. So we get some conflicting information. I will tell you, based on what I do remember about these diagnostics, rarely do you get all five that provide the same evidence. I typically go with the majority. If I were going to proceed with this model and publish it, I would want at least three of the five. If I remember correctly, we came in at only two. So I would I would conclude that our model is not well specified, and it doesn't model what's truly going on with our data. But what I want to do, instead of going out and searching for a model that does check at least three of the five boxes, I want to proceed. Well, what if it did? What do we get in the estimate below, or I'm sorry, in the output below? So you'll see compared to the other output, we have the relationship. Now let me pump the brakes, because sometimes people watch videos. My students watch videos in a row, and it might be possible that you watched the previous video yesterday and you're coming back. So what we did before is we just modeled the grit problem solving algebra predicting trig part. But for this model, I actually added in the here we go. Let's see. Yeah, I added in the calculus predicting trig. So this last part, added it in. So we're looking at the comprehensive model in this output. Now, I still using the double tildes that indicates to you that I'm looking at the that I'm asking R to provide the variance covariance output, which we'll see we get. So again, degrees of freedom greater than zero, model diagnostics here means something to us. But now we go down to the regression coefficients. Really, we get just exactly what we did before. We get the one model predicting trig. We get the model that we just added, taking trig as a predictor, predicting calculus. And then we get the covariances of each of the models. And you'll see that the variance structure that's presented is exactly as before, but we're given this calculus line, which allows us to get into the other parameter. Now, the R squared is quite interesting because we have two entries here. And the calculus just says that 55.2% of the variance in calculus is explained by the regression on trig. And as we talked about in a previous video, the 51.4 says that the similar statement for trig. Now, I did all this previously, so I'm not going to go through that. But now, once I have my model specified, in our case, not well, I would want to start creating a path output. Now, there's a couple of ways that I'm going to demonstrate here. I don't like either one of them for reasons I'll explain along the way. But the first one, if you install packages simplot, you see that I got sloppy there and didn't put that in quotations. Now, I will tell you, when I first started messing around with SEM's path analysis and I tried to install a couple of these packages, R would completely quit, just kick out. And I ended up having to delete the version of R that I had and install the most updated one to get these packages to work. So that may happen for you. So if I run install the packages, the package simplot, and then if I access the library, and I can add uh, run this command right here. So let's just copy and paste that down here, and I'll show you what happens. This is the one I prefer least, and it may become clear. So what it gives us the path coefficients, the standardized path coefficients. It gives us, of course, the covariances, but it doesn't give us the variances. And I don't like the way that this output uh, is presented, but it's one that I wanted to demonstrate to you. Another one that I used, I again have to install Lavon plot. We use Lavon to actually run the model. I chose no here in terms of running the source packages, um, and then access the library. So let's go get it. So I have Lavon plot for my model, and I entered in some other stuff, some other defaults, and so I'll just run this. I prefer this one a little bit over uh, the SEM plot. You can see what it gives us. It gives us the endogenous or exogenous variables. It gives us the standardized, no. The two arrow output are the covariances, and the one arrow would be the standardized path coefficients. It's a little cleaner. I learned all this using Amos, which is a package through SPSS, which actually, in my opinion, just destroys the quality of these packages in R. But Amos has gotten quite expensive. Now I think it's worthwhile to do this. Let's go back to our output and let me show you where these things come from. If you have an arrow, so from algebra to grit, and we have this path with two arrows, this 12.64 tells me that's the covariance between algebra and grit. So if we come to covariances of grit algebra, we get the 12 point, I didn't round very well, did they? It should be 12.65, but no, I'm sorry. That will be the, let's focus on this std.lv. And again, for the covariances, it's the same, so it won't matter. We should have circles for the variance, 33.184 for trig. So we should have a circle there that we want to add to represent the variance. Now, the path coefficient, if we look from algebra to trig, we'll go to our regression coefficient. So algebra to trig, we can see that the standard.lv, interesting. These estimates are the standard, so standardized path coefficients. I did not know that, I have to admit. So actually this right here, we don't need. Interesting. I didn't appreciate that. Didn't appreciate it because I didn't know it. All right, so from trig to calculus, 0.32. Come to our path coefficient from trig to calculus, we'll see that, well, shoot, I can depend on that, right? So that's what we would get. So I would want to take that information. If it was me, I'd want to create this in PowerPoint. Actually does a pretty nice job creating the arrows and for the covariance and the circles for the variance and the disturbance terms. So we would want to put that information. So from trig to calculus, I would want to put 0.32, 3 asterisk to indicate statistical significance at the 0.001 level. So I'd want to take that information and put it in this format. Again, if you got the extra cash, I forget, I don't know what SPSS is going for these days, but Amos, AMOS, is exceptional for path analysis. All right, I would say I don't think I'm going to go much further on this. If someone stops you on the road going home tonight and say, "Well, I know you're taking Darbro's quant methods class. I know you're studying SEM's path analysis. I assume you're an expert. Don't do that. You're not. You know enough right now just to be dangerous." But the purpose is not to teach a semester-long class in SEM path analysis, although I think that would be really, really, really fun and interesting to do. It's just to give you a brief presentation that um, of this statistical technique that is out there that does model causation. All right. So what do we? I don't think we've talked yet about assumptions. I think I talked about it maybe in the first video, but I think it would be worth just mentioning it here. Um, so again, let's pump the brakes. What we do is with this statistical procedure, we're able to test certain theoretical statements and and I don't know, maybe examine like presumed causal chains of variables. It's the only statistical technique where we can really appropriately use the word causation as an outcome. Um, Another approach is we could just create two regression models. One regression model would use the multiple predictors into trig, and the other regression model would have trig predicting calculus. The problem with that is we don't get these model diagnostics of the overall relationship where we have a dependent variable for this component being a predictor independent variable for this component. So we don't get these model diagnostics. So that's one drawback and a significant one as well. Um, Assumptions, same as multiple regression. We want our residuals to be normally distributed. We want equal variance. Uh, I will tell you that you cannot use dummy variables in path analysis. You can use dichotomous variables. For example, if you're conducting a study and you code uh, gender is just by dichotomous, male and female, then you could use that in this process. If you have male, female, and maybe non-binary, then you cannot. So if we have a categorical predictor, uh, uh, with more than two levels, we can't use. So we ultimately want continuous variables. We want things free of measurement error. So we feel like we can check that box if we have variables that were observed. Now, when we get into latent variables, that's a different situation there. Although we do kind of proceed sometimes assuming with latent variables, assuming free of measurement error. We want these things to be recursive. In other words, when we read from left to right or up or down, whatever direction we're going, we don't want any looping back. So I don't want an arrow here going back from calculus to trig. We assume the residual error terms are not correlated. So these residual errors for trig and calculus, we do not want those to be correlated. And there's something else. I forget what it is. I should write this stuff down. Sometimes I depend too much on memory. Shoot, what is it? Okay. We want our terms to be additive, which, by the code that we've used, we clearly have additive terms. All right, gang, I guess that's it. I feel like it's one of those situations where I feel like I'm forgetting to share something, but I don't know yet whether I'm going to put up post another example. I don't think I am, and I'll tell you why. I want to share this with you. We're in lesson 7. We're getting ready to end the term. You're getting ready to have an exam or a final project, plus probably an assignment and a discussion forum post, most in a 7-week term, like we teach when I'm posting this video, instructional video, there's a lot going on at the end. So I want to try to keep this as brief as possible. It would be brief if I'd stop talking. All right, take care.